12 stops on this chapter's route. The population model, least squares from criterion to formula, interpretation, uncertainty, inference under ideal errors, robust inference when they fail, data generating processes with Monte Carlo, and the mistakes, assumptions, and formulas that hold it together. Your goals: write the population model and explain its error term, interpret both coefficients for continuous and binary regressors, state the central limit theorem for the slope, compute standard errors, t-statistics, and intervals, use robust standard errors when needed, and run Monte Carlo studies. Chapter 2 gave us point estimates. Intercept 0.99, slope 0.017. The problem, stated plainly on this page, a different random sample of 1,000 apartments would yield different numbers. Chapter 5's goal is the sampling distribution of the slope estimator, and its key tool is the central limit theorem applied to least squares. For large samples, the estimated slope is approximately normal around the true slope. We know what we estimated. This chapter tells us how certain to be. Set the scene once more. Each extra square metre is associated with 17,000 kroner of price in this sample. Another 1,000 sales would say something slightly different. The goal for everything that follows: make statements about the population, not just the sample in hand. Here is the population model. Y equals an intercept, plus a slope times x, plus an error term u, and immediately, the most important distinction of the chapter. Read as a linear projection. The coefficients are defined so that the error is uncorrelated with the regressor by construction. That involves no assumption at all. Read as a causal or structural model. The slope is a true effect, and the condition that the error has zero conditional mean given x, exogeneity, is a genuine assumption that can fail. Most of this chapter works at the projection level. What actually lives inside you? Everything that affects price but is not size. Number of rooms, floor level, neighbourhood quality, condition, distance to transit, balcony and parking, plus any mismeasurement of the recorded price. The closing line deserves emphasis. The error term is not mystical randomness. It is information we simply do not have in our dataset. 2 levels, 2 notations. The population model wears Greek letters, fixed unknown constants and a random error, never observed directly. The sample regression wears hats, estimated coefficients, observed residuals, different values in every sample. The key message at the bottom is the chapter in one sentence. The true slope lives in the population, the estimate lives in the sample, and our task is to use one to learn about the other. The causal reading needs its assumption stated exactly. The expected error given x is 0. In words, x is exogenous. This is not automatic. At the projection level, zero covariance between regressor and error holds by construction and asserts nothing. Exogeneity is the strictly stronger conditional mean condition that causal claims require. When it fails, we get omitted variable bias, the centerpiece of Chapter 6. Make it concrete with the apartments. Let the error contain neighbourhood quality. If larger apartments sit systematically in nicer neighbourhoods, the conditional mean of the error varies with size, and least squares attributes part of the neighbourhood premium to size, a biased estimate of the pure size effect. If size is unrelated to neighbourhood quality, the condition holds and the size effect is cleanly estimated. Drawing a random sample turns the population equation into its sample counterpart, observation by observation. Over repeated sampling, the regressor and error are uncorrelated, and under random sampling, the least squares estimators are consistent for the population coefficients. The caveat matters. If sampling is not random, say only broker-sold apartments enter the data, consistency for the intended population can fail. That caveat is real in our data. The registry excludes apartments sold without a broker. If non-brokered sales differ systematically, our estimates describe brokered sales only. The honest fix is definitional. Redefine the population as brokered sales for which the estimates are valid. The lesson generalizes. The relevant population is determined jointly by the research question and by what the data can actually represent. How does least squares find the line? By minimizing the residual sum of squares, the summed squared gaps between outcomes and the line's predictions, viewed as a function of the intercept and slope. Take the two partial derivatives, set them to zero, and the closed-form formulas fall out on the next page. The formulas. The slope is the sum of cross products of deviations over the sum of squared deviations in X. Sample covariance over sample variance. The intercept anchors the line through the means, and keep the identity at the bottom in view. The slope equals the correlation times the ratio of standard deviations, the bridge between Chapter 4 and this one. Geometrically, least squares minimizes squared vertical distances, not horizontal, not perpendicular, because y is the variable we are predicting and errors are penalized in the y direction. Two exact properties follow. Residuals sum to zero, and residuals are uncorrelated with x in the sample. Note the closing phrase, by construction, not by assumption. Those properties hold in every fitted sample, meaningful or not. For continuous x under a linear conditional mean, the slope has a precise reading. The expected outcome at x plus 1 minus the expected outcome at x equals the slope, whatever x. A 1-unit increase in x is associated with an expected change of beta 1 in y. And the caution repeats because it must. Associated does not mean causes. Omitted variables may drive both. The intercept is the expected outcome at x equal to 0. Whether that is interesting depends entirely on whether 0 is a real value of x. For apartment size, it is not. No 0 square meter apartment exists, and the intercept merely anchors the line. For a binary regressor, 0 means something real, not newly produced, and the intercept becomes a group mean worth reading. Binary regressors bring a small piece of good news. With x taking only the values 0 and 1, the intercept is the mean outcome at 0. Intercept plus slope is the mean at 1, so the slope is exactly the difference in conditional means. A straight line always passes through 2 points, so no linearity assumption is needed at all. In the apartments, that difference is about minus 0.025 million. Newly produced apartments sell for roughly 25,000 krona less, size not yet held fixed. With a continuous regressor, by contrast, linearity is a genuine assumption. If the true conditional mean curves, the linear fit is still the best linear approximation, but only an approximation, and the failure is visible in the errors. Their conditional mean is systematically non-zero at some values of x. Transformations, logarithms, and polynomials handle such curvature in Chapter 7. The two panels show the failure. On the left, the true conditional mean bends while the fitted straight line cuts through it, overshooting in the tails and undershooting in the middle. On the right, the consequence for the error. Its conditional mean swings systematically positive and negative across x rather than sitting at 0. When you see that pattern in residuals, linearity is the suspect. Now, uncertainty. The estimated slope is a random variable. Different random samples give different slopes, and the distribution across samples is its sampling distribution. Knowing that distribution is what makes tests and intervals possible, and the central limit theorem for least squares delivers it. For large n, the estimated slope is approximately normal, centered on the true slope, with a variance we now need to estimate. The simplest variance formula needs spherical errors, two conditions worth naming separately. Homoscedasticity, the error variance is constant, whatever the value of x. Independence, distinct observations errors are unrelated. Both can fail in practice, and both matter differently. We start here for intuition and relax them almost immediately. The pictures show what homoscedasticity means. Left panel, constant spread around the line at every x. Right panel, the spread grows with x, heteroscedasticity, and exactly the pattern housing data tend to show. The caption's warning is the point. If the right panel describes the truth, the standard variance estimate of the slope is biased. When are errors not independent? 3 standard situations. Clustering. Students who share a classroom share a teacher, so their errors correlate within the class. Autocorrelation. This year's employment is correlated with last year's. And panel data, with repeated observations on the same unit. For cross-sectional data, without natural groupings, independence is often a reasonable assumption, which is where this chapter lives. To estimate the error variance, divide the residual sum of squares by n minus 2, because 2 parameters were estimated, costing 2 degrees of freedom, the same logic as the n minus 1 of chapter 3. Its square root is the residual standard error, the typical size of a prediction error in the units of the outcome. The variance of the estimated slope under spherical errors is the estimated error variance divided by the sum of squared deviations of x. 3 levers of precision hide in that ratio. Less noise around the line, more precise. More observations, more precise. And more spread in the regressor, more precise. The third lever is the least obvious, so it gets its own metaphor next. Think of the data points as people on a seesaw sitting at their x positions. If everyone crowds the centre, one person shifting slightly tips the plank freely. The slope is poorly pinned down. If people spread to the ends, each has leverage and the slope is firmly identified. Mathematically, the sum of squared deviations in x grows with the spread, shrinking the slope's variance. The table quantifies all 3 levers for the apartments. Baseline, 1,000 sales, standard error about 0.0014. Double the sample and it falls by the square root of 2. Halve the error variance, same improvement. Quarter the sample to 250 and the standard error doubles, widening the confidence interval to roughly plus or minus 5,500 kroner per square metre instead of 2,700. Precision is arithmetic, not magic. The intercept has its own variance formula, displayed here for completeness, and the same 3 intuitions carry over directly. Larger samples, quieter errors, and a more spread-out regressor all tighten the estimate of the intercept as well. Nothing new happens conceptually on this page. The slope remains our main character throughout the chapter. Inference now assembles itself from chapter 3's parts. Standardize. The estimated slope minus the true value over the standard error follows a t-distribution with n minus 2 degrees of freedom, exactly under normal errors, approximately for large samples otherwise. To test any hypothesized slope, compute the observed statistic against that null value. The 2-sided p-value doubles the tail beyond the observed absolute statistic, 1 line of code in R reject when it falls below the chosen level. The most common null, worth naming, a slope of 0, meaning the regressor has no linear association with the outcome. That is the hypothesis behind every star in a regression table. The confidence interval takes its usual form. Estimate plus or minus a t, critical value times the standard error, with the critical value near 1.96 for large samples at 95%. For the apartments, the slope of 0.017 carries a 90% interval from about 0.014 to 0.020. We are 90% confident an extra square metre is associated with between 14 and 20,000 kroner. The 95% construction step by step. Given slope 0.0170, standard error 0.0014, nearly 1,000 degrees of freedom. Critical value 1.962, margin about 0.0027, interval 0.0143 to 0.0197, 14,300 to 19,700 kroner per square meter. And mind the caution, this interval is for the population parameter, not for any individual apartment's price change. In R, the entire inferential toolkit sits in the summary of the fitted model. The coefficient table holds estimate, standard error, t-value, and p-value, each extractable by name, and the confidence interval function delivers any level directly. Here, the 90% interval from 0.014 to 0.020. Python's stats models mirrors the whole exercise, fit with the formula interface, print the full summary table, then read the parameters, standard errors, t-values and p-values by name, with the interval method taking whatever level you choose. Two languages, the same numbers, and the same names attached to the same statistical objects. Here is the numerical table for the living area regression. Intercept 0.990, standard error 0.101, t nearly 10, slope 0.017, standard error 0.001, t about 12.4. Both p-values are far below 1 in 1,000. A t of 12 means the estimate sits 12 standard errors from 0. Essentially impossible under the no association null. This is exactly how R prints it. The coefficient block with estimates, standard errors, t-values and p-values, decorated with significant stars. Both coefficients here earn 3 stars, significance at the 1 in 1,000 level. Learn to read this block fluently. Every empirical paper you encounter is built from tables like it. One page to decode the columns once and for all. Estimate, the best guess of the population parameter. Standard error, its uncertainty. The t-value, estimate over standard error, testing the zero null. The probability column, the two-sided p-value. And the stars, shorthand for 5%, 1%, and 0.1% thresholds. Nothing more, nothing less. When does the intercept matter? Two cases from our data. With living area as the regressor, the intercept of 0.99 million is the expected price of a 0 square meter apartment, meaningless, an anchor for the line and nothing else. With the new production indicator, the intercept of about 2.114 million is the expected price of a non-new apartment, meaningful and interesting. The rule: interpret the intercept only when 0 is a realistic value of x. Units discipline the slope. 0.017 million kroner per square meter converts to 17,000 kroner per square meter, and the correct sentence is, each additional square meter is associated with an expected price 17,000 kroner higher. What not to say is listed for a reason, not causes, which awaits chapter 13. Not for this apartment, adding a meter raises its price because the slope describes population averages, and never a number without its units. Heteroscedasticity is not exotic, it is the norm in economics. Housing price variance grows with size and price level. High-income individuals have more variable outcomes. When the conditional error variance is not constant, the simple variance estimate of the slope is biased. Standard errors may be too large or too small, and tests and intervals stop being reliable. The good news survives. The point estimates themselves remain consistent. The repair is the Eicher-Huber-White robust estimator, the sandwich formula displayed here. Squared deviations of x weighted by squared residuals over the squared sum of squared deviations. It assumes nothing about constant variance and is consistent whether or not the errors are homoscedastic. Its square root is the robust standard error, and it will be our default in large samples. For the apartments, the comparison is instructive. The robust standard error for the slope is 0.0017 against the classical 0.0014, about 20% larger, and the intercepts grows similarly. The robust t drops from 12.1 to 10.0, still overwhelming, but honestly so. Using classical standard errors here would understate uncertainty, and the rule at the bottom follows. With large samples, use robust standard errors unless you have strong reasons for homoscedasticity. Why not robust always and everywhere? Because the robust estimator has worse small sample properties. It can underestimate the standard error in small samples and over-reject true nulls. In large samples under homoscedasticity, the two estimators coincide anyway. Hence the rule of thumb, large N, always report robust, small n, classical may be preferable when homoscedasticity is plausible. The two estimators are relatives, not rivals. If errors are homoscedastic, the squared residuals hover around a common variance, and the sandwich formula collapses algebraically into the classical one. The robust estimator nests the classical as a special case, which is exactly why it costs so little to use it by default. In R, robust inference takes two packages and one line. Fit the model as usual, then ask for the coefficient test with the heteroscedasticity consistent covariance. For the apartment data, the robust standard errors come out larger than the classical ones, consistent with the heteroscedasticity we saw in the price scatter. Python builds it into the fitted object. Request the robust covariance results with the basic heteroscedasticity consistent type and print the summary. The variants with finite sample corrections are one keyword away. Whichever language, the mechanics are deliberately boring. The judgment lies in choosing to use them. Why simulate? Because in practice we never know the true data-generating process, but we can posit one, sample from it repeatedly, apply our estimator, and study the sampling distribution that results. That is Monte Carlo simulation, and it earns its keep three ways: checking whether standard errors are correctly sized, watching inference break when assumptions fail, and seeing sample size do its work. Here is a deliberately challenging data-generating process. Y equals 0.3 plus 0.2 times x times e, where x is uniform on the unit interval and e has a chi-squared distribution. The regression coefficients are exactly 0.3 and 0.2, but the implied error is both non-normal and heteroscedastic. With classical standard errors and a small sample, the t-test should misbehave, and now we can watch it do so. The R simulation runs 10,000 replications at a sample size of 30. Draw X, draw the skewed error, build Y, regress, and store the t statistic for the true slope. Two summary numbers and a histogram then tell the whole story, and they appear on the next page. If classical theory held, the t statistics would average 0 with variance near 1 and a symmetric shape. The simulation says otherwise. Mean about minus 0.35, variance about 1.8, and a visibly skewed distribution. The test is badly calibrated. Nominal 5% rejections will not be 5%. Increasing the sample size and switching to robust standard errors restores calibration. The lesson compresses well. Small samples plus non-normal errors plus heteroscedasticity equals unreliable classical inference. Large samples rescue us through the central limit theorem and robust standard errors. The data-generating framework makes all of this precise and quantifiable, and even though the real process is unknown, simulating plausible ones calibrates how much to trust our inference. First pitfall, the perennial one. Wrong. The p-value is the probability that the slope is 0. Correct. The p-value is the probability of a t-statistic at least as extreme as observed, computed assuming the null is true. It is a statement about the data given the null, never about the null given the data. Second pitfall, reading a large p-value as proof of no effect. Failing to reject does not establish a zero slope. The test may simply lack power. Our new production coefficient is the live example, estimated at minus 0.025 million, but with a large standard error. That is, lack of precision, not evidence of a zero difference. Report estimates and intervals, not just p-values. Third pitfall, units. Measure price in millions, and the slope is 0.017. Measure it in kroner, and the slope is 17,000. Same relationship, wildly different numbers. Any coefficient quoted without units is uninterpretable, so always state the units of both variables. Fourth pitfall, the one that opens the next chapter. The simple regression slope picks up everything correlated with both x and y. Rooms correlate with size, omit rooms, and part of the room's effect masquerades as the size effect. That is, omitted variable bias, and Chapter 6 is devoted to it. This assumptions table is the chapter's spine, worth a slow read. Random sampling buys consistency. Its violation biases estimates. Exogeneity buys the causal reading. Its violation is omitted variable bias. Homoscedasticity and independence underwrite the simple standard error formula. Their violations call for robust and clustered standard errors respectively. Normality is strong and buys exact small sample t distributions. The central limit theorem covers us in large samples. Practice follows the bottom line. Large N needs random sampling, exogeneity, robust standard errors. The summary in 7 lines. The population model defines the coefficients as best linear predictors. Least squares is consistent under random sampling. The central limit theorem makes the slope asymptotically normal. The spherical error variance formula. T-tests and intervals with n-2 degrees of freedom. Robust standard errors for heteroscedasticity, needing large samples, and Monte Carlo as the microscope on all of it. 5 formulas earn a permanent card. The error variance as residual sum of squares over n-2. The classical standard error of the slope. Its robust sandwich counterpart. The t-statistic against any null, and the confidence interval, estimate plus or minus critical value times standard error. Everything else in the chapter is commentary on these 5 lines. 4 discussion questions, and the 4th is the trap. With all of the registry's records from that year, is there really no sampling uncertainty? Bring Chapter 4's superpopulation argument to bear before you answer. The complete R workflow fits on one screen. Read the data, fit the model, print the classical summary, request robust coefficient tests through the sandwich covariance, and obtain the classical confidence interval shown here. For final large sample reporting, pair the estimates with robust standard errors and robust intervals, and, the Python twin of that workflow, fit the model with stats models, print the classical summary first, then request the robust covariance results, and read confidence intervals from either object, here at the 90% level. Keep both workflows within arm's reach. The course will reuse them almost unchanged in every chapter that follows. The first exercise takes the municipality's data. Regress the tax base on the tertiary schooling share, build the error variance and standard error by hand, form the interval, then decide, with a residual plot, whether classical or robust standard errors belong here. The second exercise returns to the apartments, now with the monthly fee as outcome. Interpret both coefficients with units, predict the fee for 50 square meters, check linearity with a scatter, compare robust against classical standard errors, and build a 99% interval. The third exercise regresses the share of young residents on municipality population, and its heart is diagnostic. Explain why homoscedasticity is likely violated. See it in the residual plot. Compare the 2 standard errors and defend which one you would report. The fourth exercise reruns the chapter's Monte Carlo at 3 sample sizes, asking when the t-statistics become calibrated, mean near 0, variance near 1, and how much sooner robust standard errors get you there. This table places the chapter in the arc of the book. The correlation t-test of chapter 4 is identical to the slope t-test here. Multiple regression extends everything to many regressors. Nonlinear models transform variables inside the same framework. Clustered errors replace the robust estimator when errors group. Prediction intervals and cross-validation arrive with chapter 10. And causality asks when the slope earns a causal reading. The chapter 4 identity deserves its algebra. The slope equals the correlation times the ratio of standard deviations. Substitute that and the classical standard error into the t-statistic, simplify, and everything collapses to the correlation ET, statistic with n-2 degrees of freedom. Testing a zero slope and testing zero correlation are one and the same test. Scaling behaves predictably, and the table settles it. Multiply the outcome by a constant. The slope scales with it. Multiply the regressor. The slope divides by it. Add constants, only the intercept moves. And in every row, the t-statistic and p-value are untouched. The substance is invariant, only the units change, which is why stating them is non-negotiable. A graphical test strategy for homoscedasticity. 4 steps. Fit the regression, save the residuals, plot them against fitted values, then plot their absolute values the same way. If the spread grows along the horizontal axis, heteroscedasticity is present. Formal tests exist, Brush and Pagan, white, but visual inspection is usually sufficient, and the default recommendation stands regardless. With large samples, robust standard errors, the 2 panels rehearse the diagnosis one more time. On the left, residual spread roughly constant across the range, the homoscedastic ideal. On the right, spread growing steadily with X, which is what price data typically look like. Train your eye on the right panel. It is the one you will meet in practice. A numerical example closes the loop on binary regressors. Price on new production status. The non-new intercept is 2.114 million with a standard error of 0.048. The new production coefficient is minus 0.025 million. So newly produced apartments sell for 25,000 kroner less on average. Its standard error is 0.202, giving a t-statistic near minus 0.13 and a p-value near 0.90. We cannot reject a zero difference. That reflects limited precision, not proof that the difference is 0. 6 takeaways to carry forward. The population model frames regression as a best linear predictor, not a sample quantity. Random sampling gives consistency, and the central limit theorem gives asymptotic normality. Precision has 3 levers: sample size, error variance, regressor spread. Spherical errors justify the simple formula. Heteroscedasticity calls for robust standard errors. Monte Carlo makes the theory concrete, and always report the full picture. Estimate, robust standard error, interval, never the p-value alone.